First about the seminar itself. What happened was 2 weeks ago, 1.5 weeks ago, I measured CO2 and it was in the Friday seminar room and it was pretty high, so I reported that. So health and safety got back to me first saying we're going to fix this problem, we're going to fix the ventilation. That was the first story that they told, and the second story was we can't fix the isolation, the ventilation. We're going to close the room. So that is what I responded to. The final story that they're telling is that there was never a problem with the ventilation, and my CO2 measurements are wrong. So that is their position at the moment. I think a lot of what is going on in this university can be explained by Adam Tickell's desire for a knighthood. We're following very slavish, even though we are an independent institution, we're following the government, even though the government is entirely incompetent, very, very slavishly. And that explains part of what is going on, and we also seem to be reaching the same level of incompetence in some areas. That said, there's also a large number of students who say they cannot make it to these seminars. Again, the university's message there is that you guys online, you are lying, because at the university as a whole there's only 28 students who are self-isolating, which of course implies that the incidence at the university is 3 times as high as the national incidence, which is 10 times as high as what you see on the continent. But those 28 students seem to be all in this class, is the message that I get from the university, which I find unlikely. Now, in order to accommodate both problems, both the room problem and the fact that people seem genuinely frightened or unable to come to campus.
Which room had the CO2 problem?
It's Freeman 31, yeah,
Oh.
G31. The solution is to move the Friday seminar online and keep the Thursday seminars face to face, so that the people in the Thursday seminars who can't be there physically can move to Friday, and the people who attend the Friday seminar, if you want to do it face to face, can move to one of the Thursday seminars. Does this meet any objections, insurmountable objections from you guys? No? The alternative would have been, but there was no enthusiasm at all, to do a seminar at 7 or 8 at night when there's no conflict with your university timetable. Although you may have had other plans for those evenings, right? And I definitely had other plans for those evenings. So that is what we're going to do. For now, and when the university sorts out this mess, what is going on in this room, and maybe case numbers will abate over the next weeks, although I wouldn't count on that. We probably going to revisit this during the reading week to see whether you want to keep up this schedule or go back to the original one. Okay, is that clear to everybody? Yeah? So, today I'm going to talk about decision analysis. Because of the decision analysis, it's sort of strangely in the sequence. It would make sense to do it immediately after the discussion of externalities and public goods. It also would make sense to do it immediately after the valuation sequence. But because of the essay and because of the reading week, the valuation sequence has been pushed towards the back of the module. So some of the things that I'm going to talk about sort of presume that you have followed weeks 7, 8, and 9 but hopefully that won't be too much of an issue. I won't make a big deal of that. And I'm going to talk about 3 chapters essentially. I'm going to talk about efficient flow pollution, I'm going to talk about efficient stock pollution, and we're going to talk about alternatives to cost-benefit analysis. And I'm going to show you an application, just to make it more concrete. Now, the whole reason for decision analysis or project appraisal or whatever you want to call it can probably be summed up by this quote from Robert Solow. Economists have the reputation of being unimaginative bean counters, doggedly claiming to quantify the unquantifiable and personifying Oscar Wilde's definition of a cynic as someone who knows the price of everything and the value of nothing. It is true that they would give a lot for a rough quantitative answer, but it only reflects the fact that any policy can be pushed harder or less hard, further or less far, and that a useful evaluation has to suggest how hard and how far. The beans have to be counted if only approximately. So far, so uncontroversial, but this is Solow. Those gentle souls who merely ooh and ah over them are arguably part of the problem, not part of the solution. So the whole idea is to put some structure on decisions that are made, that instead of making random decisions or ill-informed decisions, you make an attempt to at least quantify everything and find a rational basis for the decision that you're making. This is true and important for your personal life, and instead of deciding randomly, you think about the decisions that you make. But from the public perspective, from a government's perspective, it is even more important because, of course, we pretend to live in a democracy, and one of the hallmarks of democracy is that the government can explain the decisions that it made. That is part of the accountability of government, right? And you can only explain yourself if you have indeed thought about the decisions that you made. And this is all part of it. Abraham Lincoln said it more succinctly. The true rule in determining to embrace or reject anything is not whether it has any evil in it, but whether it have more evil than of good. This is somewhat older English, right? So the issue is not that there is a project and there's something wrong with the project. The issue is to find sometimes the least of all evils, and sometimes you find something good. If there is a project that is completely uncontroversial, that has no downsides and only upsides, then of course you should just do it, right? Then there should not be any debate whatsoever. But there's very few interventions that actually have this. And Johan Cruyff said it perhaps most succinctly, that every upside has its downside. And the whole purpose of cost-benefit analysis is to find those trade-offs, right? And quantify those trade-offs and then find the best course of action. So, I'm going to talk about pollution. Pollution is an externality. It's an unintended, uncompensated impact on a third party. Now, pollution depends on many things. And if you want to solve a problem, you need to understand a problem first. And that drives part of what you would do. And pollution depends on many things. One of those things is environmental transport and assimilation. So if you burn coal or oil to make electricity, particularly diesel, that coal is never pure. It's never purely carbohydrates. There's always other stuff in it. And one of the things that is in there is sulfur. So if you burn coal to heat your home or make electricity, that sulfur is released into the atmosphere. That sulfur is oxidized. It becomes SO2. And SO2 is completely innocent. and doesn't harm anybody. But then when that SO2 sort of travels through the atmosphere, it meets other stuff in the atmosphere, particularly hydrogen radicals, and then it reacts with those things and it becomes sulfuric acid. And that acid then gets deposited, either in rain, and then it's called acid rain, or it may just fall out of the sky. And it's in that form that it is harmful, right? And this transformation is important because something that started off as essentially an innocent part of the coal became another innocent part of the atmosphere, and then through a chemical transformation it turned into something that is harmful. And acidic deposition hurts plants, particularly trees, it hurts fish, and it hurts limestone. So all our cathedrals and monuments and everything get slowly dissolved in the acidic air. And those of you who think that those old cathedrals look so very blurred nowadays, that is because they are so very old. No, that is not true. They were pristine for the first 600 years of their existence until we started burning coal at a large scale. It's only then when they became as they are now. So these things are important. Another important thing about sulfur is that because these transformations take a while, the source of the pollution and its eventual consequences can be hundreds, sometimes thousands of kilometers apart. So it's not the immediate surroundings of the coal-fired power plant that suffer from acid rain, but it is, depending on the winds in Europe are mostly west, so the coal that is burned in England falls mostly on Germany and Poland, right? So these things are important. Another thing that is important is what is the background concentration. A little bit of sulfur does hardly do any harm, but if there is already a lot of acid rain, then the additional acid rain actually can push ecosystems over the edge and can do a lot of harm. Of course, once you have killed everything, then adding more sulfur to the system doesn't do any harm because there's nothing left to damage, right? So the background concentration matters, and these are often very non-linear processes, right? So those things need to be kept in mind when you're talking about pollution. What are you actually talking about? Where does it come from? How is it transformed? How does it start to become something harmful? And of course, also once it has been absorbed by plants and by fish and so on and so forth, the sulfur doesn't do any further harm, right? It has been neutralized at the expense of the trees, but the sulfur itself has now been neutralized. So those things are important. Another important distinction, and one that I will make much more of, is the distinction between flow and stock pollution. The extreme example of flow pollution is noise. If your neighbor works in construction, has to get up at 5 in the morning to get to the construction site, gets out of bed, has breakfast, starts his engine, wakes you up, right? That is very annoying. But as soon as the car has left the street, the noise is gone, right? This is the activity and the annoyance are very tightly tied in time. This is a flow pollutant. As soon as the activity stops, the pollution is gone. You may still be in bed being annoyed that you've been woken up, but the source is gone. The canonical example of stock pollution is nuclear waste. If you use nuclear power to make electricity, then the reactions in your power plant will lead to nuclear waste, and that will be radioactive depending on the substance you're talking about. 5,000 years, 10,000 years, sometimes 20,000 years. So even if we stop all nuclear power production today, we will still have a nuclear waste problem in 10,000 years' time, right? That is a stock pollution, right? Of course, most things are somewhere in between, and lifetimes vary. Now, how would you set a target for a flow pollutant? I'm going to show you two derivations. First, going to do it algebraically. That's not true. This is calculus, not algebra. First, going to do it with calculus, and then I'm going to do it graphically. So let's assume that the damages of pollution are given by D, and M for emission are our pollutants, right? So that is the damage that is done by the pollution. The benefits of the polluting activity are denoted by B, and for simplicity I also assume that that is a function of M. Now there has to be benefits of the polluting activity, because otherwise there's no trade-off, right? If something does harm but does no good, then you should just stop doing it. But going back to the sulfur example, so this would be the damages of acid rain, the trees that are killed, the fish that are killed, and so on and so forth, the monuments that are damaged, and these would be the benefits, and the benefits are electricity, cheap electricity, and reliable electricity, right? The net benefits are then just benefits minus costs, and that is what you would want to maximize, right? Now, this is a simple unconstrained optimization problem. So you would find the optimum by setting the first partial derivative to 0, right? You are familiar with this. The first partial derivative is the first partial derivative of what you care about, the net benefits, to what you can control, the emissions, right? So it's always your objective function to your decision variable. So D and B, dm must equal 0. D and B, our NB is the sum of benefits and costs, or benefits minus costs even. So that is first partial derivative of the benefits to the emissions minus the first partial derivative of the damages to the emissions. We bring one of them to the other side of the equation, and what we have, lo and behold, that the marginal benefits of generating electricity should equal the marginal costs of suffering acid rain, right? So a simple rule, right? And it's a simple equimarginal principle. We can also do this graphically. So on the vertical axis we have the gain. We assume that that is measured in some way. And we have emissions on the horizontal axis. And then this is our private gain. And at some point, I mean, electricity is good, right? But at some point, we're going to stop using electricity because we have charged our phones, and the house is fully lighted, and the television is on, and the oven is on, and we don't have anything more to use electricity. But electricity costs money, so at some point we're going to stop using electricity, right? At some point we are using enough electricity. So at some point these private gains from the polluting activity has to come down, because at some point we're gonna not do any more of it, right? So that means that the marginal private gains look something like this. That is this curve here, and then this Q prime that you see is the optimal amount of emissions if there were no regulations and if there were no damages, right? And that is where the total gain curve goes flat or the marginal gain curve goes through zero. Now, there's also external costs from this polluting activity that is given here in the green line. And if you add up those two lines, you find the red line. And this is the net gains from emissions. So there's positive sides, cheap electricity, and negative sides, that is acid rain. And the question is, where does this curve find its optimum? Well, where it goes flat. So you take the marginal, you take the slopes of the curves, and you can look at this in two ways. Either you can look at the point where the net gains, the marginal net gains are zero, which is the same as where the marginal damages equal the marginal benefits, right? That just happens, well, not happens, that is by construction at the same point. Right? Now, that implies that there are, I'm too fast. So the optimal level of emissions is this Q star here. This is the unregulated amount of emissions, Q prime, and this is the optimal level of emissions, Q star. And then there's areas there that we can call A, B, C, and D, but let's give them better names. This area B here, that is the optimal level of the externality, the right amount of pollution. And as soon as you say this, environmentalists get very cross with you that there is an optimal level of pollution and it's greater than zero. But that is because there's also benefits from the polluting activity, right? That is why the optimal pollution is greater than zero. So that is the area B. And this is the welfare loss associated with the pollution, because it's the area under the marginal curve. A plus B, that is this area here, that is the optimal level of the private benefits of the polluter. Again, it's an integral under the curve, right? So this is how much we gain from the polluting activity, and this is how much we lose from the pollution. So the net benefit is the area between the curves, that is A. Again, environmentalists get upset when you say this, and essentially what this shows is that there's a net benefit from pollution, right? And actually the polluting activity leads to a net gain in social welfare, namely A, and that the polluters gain A plus B, it is greater than the loss, right? The loss B. So there is a transfer essentially from the environment to the polluter. But this is what cost-benefit analysis would do, right? It tends to upset people. The area C plus D, this area here, that's the unwarranted gains from pollution, right? Those are, if there's no regulation, this is how much extra the polluters would gain in welfare. And the area D, no. The area C is how much the polluters would gain from unregulated pollution. And the area C plus D is the total amount of extra pollution that comes from the difference between unregulated and the regulated level of pollution. So there are unwarranted benefits of pollution, but they are smaller than the additional gains, right? Because otherwise we would not be in the social optimum, right? So, optimal pollution, optimal flow pollution is greater than 0. The laws of thermodynamics imply that 0 pollution implies 0 activity. That is, there's always a waste of energy, there's always a waste of material. That's simply the second law of thermodynamics, right? Entropy must increase. So to bring pollution to 0, you essentially have to stop everything. And that partly explains why optimal pollution is greater than 0. Now, some people have said, yeah, but what about the simulative capacity? What if there is an amount of pollution that doesn't do any harm, that there is a threshold effect? Well, then the curve would look like this. Essentially what you're saying in the curve that I showed you previously, the first bit of emissions, the first bit of pollution does damage, and the more you pollute, the more damage you do at the margin, right? And then you would go, the optimal point is here. Now if you say, well, the first bit of pollution doesn't do any damage because it's just absorbed by nature without doing any harm, then the curve doesn't go through the origin, the green curve doesn't go through the origin, but it goes to a point somewhere right of the origin. And if the slope of the curve is then the same, then the optimum is here. And if you introduce a simulative capacity, if you say, well, the first bit of pollution doesn't do any harm, you actually can emit more. And the optimal level of emissions, that's on the vertical axis, on the horizontal axis, shifts to the right. That is, you emit more. Right? So optimal pollution is also greater than the assimilative capacity. This just follows from the logic of optimization and from the assumption that the polluting activity does do some good to some people, right? That is a genuine trade-off to be made. Okay. This is absolutely the best way to wind up environmentalists, to just point out these fairly simple facts that just follows from the calculus invented by Newton and Leibniz. Let's turn to stock pollution. The benefits of the polluting activity are as they were. I assume that they are a flow and they depend on the emissions M. The damages of the stock of the pollution now do not depend on M, not on the emissions, but on A, and A is the stock of pollutants, where that stock is governed by a first order difference equation. That is, the stock of pollution at time t depends on the stock in the previous period at time t minus 1, and then part of the stock of pollution has disappeared, delta, where we assume that it's broken down by some biological or chemical or physical process. So part of the problem disappears over time, and the fraction that disappears is delta. But of course we've added to the problem through our emissions M, right? So the current benefits are still the same. It's the benefit of the polluting activity minus its costs. But we now have a dynamic problem. So we're no longer interested in maximizing the current benefits, net benefits, but we have to look at the net present value of those benefits, right? Or the present value of the net benefits. Net present value is defined as the sum over t. That's this sign here, summation of the benefits minus the costs. And then of course we have to apply a discount rate, and the discount rate here is rho. And then 1 over 1 plus rho to the power t is the discount factor. Now if you take the first partial derivative of this thing to the thing that we decide upon, that is m, but now m at every point in time, we get this expression here, that the marginal benefit, the present one, so we have to multiply it with the discount factor, should equal the marginal damage. But the damage is now no longer a simple expression. What this says is that it's the marginal damage at some point in the future of a slight increase in the concentration. And that slight increase in the concentration at time t plus s in the future depends on the increase in emissions at time t, right? So this essentially says if we increase emissions at time t, concentrations at time t plus s go up by this amount. And if we increase concentrations at time t plus s, our damages at time t plus s go up by this amount, right? That is what is going on here. And then of course that needs to be discounted. And at that point the discount factor is 1 over 1 plus rho to the power t plus s. And this occurs over a period of time. So we need to accumulate this from time t onwards into the indefinite future. Right? So instead of equating the marginal benefit of the polluting activity to its marginal damage, we now equate the marginal benefit to the stream of future marginal damages discounted to the point of emission, time of emission, right? Now this is awkward because we also don't just need to do this at one point in time, but we have to do this for all time t. So let's simplify things. And the first simplification is that we actually know what is going on with dA dm. So if we put 100 tons of sulfur into the atmosphere today, and this delta is 0.01, 1% of that is removed every year. And if you put 100 tons of SO2 in the atmosphere today, then in a year 99 ton remains. And then in 2 years, 99, slightly more than 98 remains. And in 2 years, slightly more than, and 3 years, slightly more than 97 remains, and so on and so forth, right? So we actually know what this is because I assumed a simple linear difference equation. So that is 1 plus delta to the power s. That is the fraction that remains. So that simplifies things a little bit. And then 1 plus delta to the power s times 1 plus rho to the power s is approximately equal to 1 over 1 plus delta plus rho to the power s. So that's already something. Now the second step I'm going to make is I'm going to put the whole thing in its steady state. And a steady state essentially means that nothing changes, and that means that instead of having the stock of pollutants at time t, it's the same everywhere, so I might as well drop my t, right? So I set AT equal to A. Now, the stock equation is AT is 1 minus delta AT minus 1 plus MT minus 1, but now we're in the steady state, so we drop the subscripts. So instead of having 3 variables here, AT minus 1 and MT minus 1, I now have 2 variables, A, and M. So things are simpler, and that of course means that we can we can rewrite this as A is M over delta. It also means that this expression here no longer depends on time, right? Because everything is the same in every period. So we can bring that in front of the equation, or in front of the summation, sorry, because it's no longer time dependent. Now, you know this expression here, this is something you recall from calculus. This is one of the standard series, x to the power a, or typically it's x to the power a, where you sum over a. This expression here, this infinite sum, can be rewritten as 1 over 1 minus the thing that we raise the power to, right? So this sum here that may have intimidated you really becomes 1 plus delta plus rho over delta plus rho. And furthermore, we have that A is M over delta, so the D, the A, can be rewritten as the D, the M times delta. And now we have this expression here. And this, you may recall, is the same expression we had in for the flow pollutant, that we set the marginal benefits of the polluting activity equal to its marginal damages in emissions, no longer in the stock of pollutants. But because we are a stock pollutant, we have to correct with this factor here, delta times 1 plus delta plus rho over delta plus rho. Conceptually, nothing has changed, right? Stock pollutants, flow pollutants, the difference between the two is this correction factor, but conceptually it's an equimarginal principle, right? We said the marginal benefits equal to the marginal costs, where the marginal costs are now a stream of marginal costs, but if we impose certain conditions on this, certain constraints, we say it's a linear accumulation of pollutants, and we say everything is in a steady state, then it just becomes a correction factor. And it is a correction factor because it's no longer just the marginal damages today, but it's the marginal damages today into the indefinite future, right? But conceptually, nothing has changed. Marginal costs equal marginal benefits. The second insight that comes here is that this decay rate, delta, is almost interchangeable with the discount rate. We have delta plus rho enters here, right? Now, why is that? What does the discount rate do? The discount rate essentially tells you that future gains or future losses are worth less than current gains or current losses, right? That is what a discount rate does. If rho is, say, 6%, that is the interest rate that you guys pay on your student loans, then essentially this says that £100 today is worth £100. £100 in a year from now is worth £100 times 1 over 1.06, right? So that's worth roughly £94, and then £100 2 years time is worth roughly £88. Right? That is what the discount rate does. That is what the interest rate does. So you disregard, you discount future damages. That is what the rho does. The delta does the same because it enters in the same way into the equation, right? It enters into the same way, into the equation. Here am I. This is where I want to, yeah. And this is not because we discount the future because we care less about future money because of interest rates that we can get in the bank. This is so because the problem disappears. The sulfur we put into the environment today, most of it will still be there next year, but some of it will be gone. And therefore we care less about it because it's no longer there, right? And the same then goes for the year after and the year after that, right? So the decay rate or the assimilation rate of pollution in the environment acts like a discount rate. It takes the problem away over time. Right. So this is what economics would do, right? If the question is, what would the target be? How much pollution should we allow? This is the answer. It shouldn't surprise you that not everybody is keen on this. One of the main problems with what I just told you is I just posited a green curve, right? These are the marginal losses from emissions. And I did not just posit this curve, I also assumed that you could add it up to the gains. I assumed that damage to the environment is commensurate with the gains from cheap electricity. Without further ado. Now, as I said in the beginning, we're going to spend 3 weeks on exactly this question. Where does this green curve come from? But the conclusion of those 3 weeks will be that this is not easy, right? That it will not be easy to estimate the disutility of pollution. Up to the point that people completely reject economics for this particular reason. So what can you do instead? Well, there's all sorts of things that have been proposed. One alternative to cost-benefit analysis is multicriteria analysis, where instead of wanting to maximize a utility function, you do other things. Multicriteria analysis is very useful in some ways and deceptive in other ways. So the first thing you do in multicriteria analysis is exclude those projects that are obviously stupid. Those projects that are dominated in everything you care about. If you have 3 projects, A, B, and C, and project C does worse for the economy and worse for the environment and worse for the income distribution than both project A and B, then you should just throw it out, right? You should no longer consider it because it scores worse on all things you care about, right? So that is the first thing you do in multicriteria analysis. And the second thing you do in multicriteria analysis, if there's a genuine choice to be made, if upsides have their downsides, then instead of constructing sort of a microeconomic objective function or a utility function, it constructs a different utility function and maximizes that. And then the question is, of course, which is the right function which truly captures society's preferences. And we know from Arrow's impossibility theorem is that the alternative that is proposed by multicriteria analysis isn't the right utility function or welfare function either, because we know that welfare function doesn't exist. So it doesn't really gain you much. The mathematics is a lot fancier. It's fine if you're into fancy math. But it doesn't really buy you much real traction, I don't think. So this is mostly an academic exercise. In actual policy making, standards for environmental pollution are set based on the next 5 criteria. And the first one that is fairly popular is to set safe minimum standards. Or can we say maximum standards? Going back to the example of CO2 in the classroom, if it's 600, it's fine. If CO2 goes above 1,000 parts per million by volume, then you shouldn't stay too long in a room like that. If you stay in that room for 8 hours or so, you end up with a pretty hefty headache. If it goes above 1,500, then it gets worse. And if it goes above 10,000, then there is imminent risk to your health, right? You really want to get out of such a room if possible, or if you're in the submarine, and that is where these standards come from, you really want to take your submarine to the surface and get some fresh air, right? So that is a safe minimum standard, something that you should not exceed. And this is particularly useful and particularly applied to things such as food safety standards and so on and so forth. That are simply certain materials that you should not eat in too great quantities because it will kill you. The question is, of course, what is safe here, and where does the safety number come from? It doesn't come from a cost-benefit analysis. Typically what they do is they feed this material to rats, and if they feed a certain doses to rats and it kills more than 0.5% of those rats, then it is deemed unsafe, right? So you have 10,000 rats, you feed them, if 50 die, then it's safe. If more than 50 die, then it's not safe. And we are, of course, about 100 times as big as rats, so if it would kill 50 out of 10,000 rats, then it would probably kill 5 out of 100,000, 100,000 people, right? And then it's deemed safe. Although typically they then divide the number by 10 as well, so it's 5 in a million. So that is where these standards come from. And it is fairly arbitrary, right? It's arbitrary to use rats rather than other models, and the numbers that they pick for what is deemed safe is also, why did we go for 0.5%? Why not 0.6% or 0.4%, right? These are fairly arbitrary decisions, but widely accepted, right? Nobody seems to mind here, because it is, after all, about our health, right? And therefore, in these deliberations, costs do not matter. Those substances are simply banned, right? Without consideration of the costs of those bans. This is not a trade-off that is made. This is just a standard that is set. Another way of setting the standard is to say, use the best available technology. You oblige industry to pollute as little as possible. Now the problem, and again this is sort of a one-sided thing. We're not looking at the costs of the technology. We just say, well, do the best you can. We're going to set a certain standard. This other company could do it, so why can't you, right? The problem with best available technology is that if you ask an engineer to solve a problem, that engineer will solve the problem. If you want to minimize emissions, an engineer will tell you a trick to get the emissions to zero. Disregarding the costs of doing so. Engineers are very good at finding fancy solutions that cost a lot of money. So typically these best available technology standards are then attenuated by something like not exceeding excessive costs. it becomes fairly arbitrary, right? And we see this in cars, for instance, that the car has to have a certain mileage. I think it's 15 miles per gallon or so is the minimum standard. And if your car falls below that standard, then you simply cannot sell it on the European markets, right? That's a simple standard, and that's an available technology. There's cars that do much better than that. A lot of this is sort of inspired by the precautionary principle. And the precautionary principle comes in two forms. One is says that uncertainty is no excuse, and the other says that it's better safe than to be sorry. Uncertainty being no excuse is, as I said, one interpretation of the precautionary principle, and this goes back to resistance that you see in certain circles, where people would argue, well, all this environmental pollution is so uncertain, why would we want to spend money on solving this? Why don't we just wait until we learn more about the true extent of the problem, right? That's a very silly position to take, because any decision that we make is uncertain, and the consequences of any decision that we make are uncertain, and we make these decisions routinely. You got out of bed this morning not knowing what the day would bring, right? So it may have been safer to stay in bed, and some of the people who are not here made that decision. Probably not because of the safety implications, but because of other reasons. If you decide to go study economics, you don't know what the future will bring. You have your model in your head, what the implications of deciding to go study economics will be. But surveys of our first year undergraduates and comparing those results to the outcome of the people who have graduated suggest that those models are very, very wrong, and that your expectations will not be met. But yet you managed to make that decision. So the idea that we don't know the results of our decision with certainty and therefore we cannot decide is just complete nonsense. We make those decisions every day, all the time. The other interpretation of the precautionary principle is that it's better to be safe than sorry, which is intuitively appealing. But again, it's very one-sided way of looking at things, because essentially what you're saying, well, there's this one risk that I really worry about, an environmental risk, and therefore I want to minimize using this because it's risky. But the assumption there is, of course, that there's no benefits of doing this, right? And one example that comes to mind is, it's now a year old, and that is the discussion about vitamin D and whether vitamin D helps against COVID. And the knowledge about that is actually pretty, definitely a year ago, was fairly weak. And you could say, well, we don't know that it would bring any benefits, and we don't know what it would do to people, so perhaps not prescribe it, right? Let's not do things if we don't know that it will bring benefits. The problem with this sort of reasoning for vitamin D is that actually we know that it can't do harm. We don't know whether it does any good, but we definitely know that it can't do any harm. And let's just not prescribe it, therefore, was the reasoning for a long time. And not just that, but also you guys were locked up in your houses, right? And the best way of getting vitamin D is through sunshine. So the decision to go for this very strict lockdown, essentially to ask people in cities to stay indoors, was the wrong decision. Because if you go into the great outdoors, there is actually not much risk of infection, but you do get your vitamin D through the sun, and it actually helps you protect against that infection. And it's probably, instead of locking you up, you should have been sent out onto the downs, far away from other people, but outside, was, in retrospect, the better decision. And the precautionary principle here, so say, oh, don't do anything that we don't fully understand, may have been wrong. Of course, we also did not fully understand the consequences of lockdown, right? But yeah, and the precautionary principle is particularly important in European legislation with regard to the environment, because essentially what it says is that no chemical can be used until we know it is safe. No measures can be introduced until we know with reasonable certainty that it's safe, and that essentially stops innovation. And a lot of things that may improve stuff are actually bad. And one example there is in pesticides and the regulation of pesticides. So at the moment there's a number of pesticides on the market. The worst ones are banned, but the ones that are currently still allowed can be pretty bad, particularly if you're a bee. It can be pretty bad for you. And there's alternatives that have been developed by industry that are not allowed on the market based on the precautionary principle, because we don't know whether they would do any harm. But because those chemicals are not allowed on the market, those pesticides are not allowed on the market, the implication is that we keep using the old pesticides that we know, that we do know do harm, right? And the problem with applying the precautionary principle is that it's a one-sided argument. We're looking at the substance in question in isolation, and we say, ooh, this might do harm, let's not do it. But we do not think of, well, if we allow this thing, does it actually bring any good? That is removed from the equation, right? No trade-off is made. We just look at things in isolation. We just look at the harm that is done, but not at the good that might be done. And it's perhaps not, well, it's definitely not what I would do. But it is very, very common in environmental policy. Another thing that is increasingly popular at the moment is the use of, let's not do any formal decision analysis, let's call together a citizen journey and let select 100 random people, or select 100 people at random rather, and let them deliberate, and whatever they come up with, that is the right way to go, or perhaps organize this through a referendum. It's very popular. Essentially this means that the decision maker, the politician who was elected to make decisions, now just hands over that decision power to a group of 100 people and just follows whatever they recommend, right? It's sort of a way of denying your responsibility as an elected politician It's very popular now. They've made use of this in France for climate policy. They're actually running these things in the UK as well at the moment. Let's see what comes out. But there's of course no way that a group of 100 people will arrive at the right solution, right? Again, arrows in possibility. Viren will tell you that there is no right solution. Are these people the best people to decide? Well, they were randomly selected, so they probably don't know that much about the problem, and chances are they aren't the cleverest, right? And the decisions they come up with are essentially arbitrary. It's essentially a function of the group dynamics in those theories. And that is the actually the most common way of setting targets for the environment. These follow from political power plays. If it goes to Parliament, or they are decided by a small group of anonymous civil servants, if the politicians do not get involved and they make decisions that are not necessarily traceable or defendable, right? Because there is some sort of game being played somewhere in the ministry. Now, economics can come back into play, is that once the standard is set, you can do cost effectiveness analysis. That is, find the cheapest way of meeting the target. This is not good, guys. Okay. I forgot to plug in my laptop. And now we have the same problem as last week. Namely that oh God, and the implication is that the guys online cannot see my slides. You guys still can. So there's 3 applications fighting for my screen, right? That's the issue. So cost effectiveness analysis finds for any standard, for any target, the cheapest way of meeting that target. So now this screen responds to what I'm doing, but this screen and that screen doesn't anymore. And there is a chance that my thing will just switch off entirely. Am I back? Yes, I am back. Now the guys online need to come back. Yay. We're learning, right? I have half an hour left, a little bit less, to talk about an application, how to do cost-benefit analysis. Social cost-benefit analysis is essentially an analytical tool to inform decisions about interventions involving public expenditure over time. And it requires a systematic counting and evaluation of all relevant costs and benefits. And where the benefits are anything that increases human welfare, and costs are anything that decreases human welfare. Where the human here is important, right? We talked in the first week about who is included, right? The assumption here is that humans count, but other species do not. And the decisions are fairly simple. If your benefits exceed your cost, you should do it. Or if your benefit cost ratio exceeds 1, you should do it, right? It's as simple as that. That is if you have discrete projects. If you have a set of discrete options, then you rank them. If you have alternative options, then you rank them and you pick the best one. If you have a whole bunch of projects that you can do, then you rank them based on the cost-benefit on the cost-benefit ratio, and then you start with the one that has the best one, and then the next one, and then until your budget is exhausted. But if you have a continuous decision, say you want to set a tax, then you just maximize the net benefit, right? It's all part of the same thing. You can use cost-benefit analysis for all sorts of things: overall environmental policy, the appraisal of specific projects, environmental management in general, and you can do this ex ante as well as ex post. You can do this before the decision is made to see what you should do, but you could also do it after the decision is made to see whether decisions were clever. Benefit cost analysis is very popular in the UK and in the EU, in the UK and in the US, sorry, not at all popular in the EU. And some of the examples that you see here are indeed from the UK, right? And the one that I'm going to talk about at some length is the London super sewer. But first, some examples of exposed analyses. So Bob Hahn did one looking back at a whole bunch of US regulations in a 5-year period. I think this was the Clinton administration, and found that some 50% just did not pass the benefit cost test, right? That some politician was trumping the benefits and playing down the costs and pushed the project through, but then if you went back 5 years later, actually found this was a pretty dumb thing to do. David Pearce found the same thing for a lot of EU directives. But of course, it all depends on how you do the cost-benefit analysis, and I'm going to talk about that now. So what do you do in a cost-benefit analysis? Well, you start by saying, well, this is what we want to do, right? You're going to justify your intervention. We have a problem and we're going to solve it, right? That's your first step. Then in the second step, you're going to identify a portfolio of possible solutions. That is a crucial step. So you're all familiar with Heathrow, and you all know that it used to be one of the most crowded airports in the world, right? One of the busiest, most congested airports in the world. And there has been a discussion for over 70 years now on where to put the third runway at Heathrow, or a fourth runway for that matter. And that discussion has been going on for 70 years. In the official discussion of where to put the runway, one option has never been there, and that is to put it in the grounds of Windsor Castle, which, if you do it independently of government and with no special feelings towards the Queen, is actually the best place to put it, because it's good transport links, far away from almost everybody except the Queen, right, and her family. That's actually where you would want to put the runway. But it is never included in the portfolio, and this is therefore crucially important. This is a crucial part of doing a cost-benefit analysis, and one way of influencing the outcomes, if you simply deny that certain options are available or possible, you can skew your cost-benefit analysis in two particular directions, right? Then, as part of this, you also need to define a baseline. What would happen to, in this case, aviation and noise and pollution in West London without any of these projects, right? Again, what you're doing here is something that is pretty hairy. You're projecting the future. You're predicting what would happen if. And this, of course, depends on how strong is your model for predicting the future, and what are the data that go into that. The third thing you need to decide is whose benefits and whose costs that is who has standing, and I already said we're only going to look at humans, so animals don't have standing and plants don't count. But also, I mean, if you're talking about a project, you're essentially going to draw a box around this project and say, well, these are the people that count, right? And going back to Heathrow, if you just count what is going on in West London, then you would get a different answer than when you count what is going on in the whole of England or the whole of the UK. Because the noise pollution and other pollutants that come out of planes that take off and land fall predominantly on West London. But the benefits of less costly, less congested aviation fall on the whole country, right? So if you do a cost-benefit analysis, what would an expanded Heathrow mean for West London? You get a different answer than when you do a cost-benefit analysis, what would this mean for England or for the UK, right? So the decision, this is again a fairly arbitrary decision, who counts matters, right? And of course the first example that I gave, who counts most, also matters, and that is the Queen. And the fourth step is again, what are we going to include? Just the noise, also the particulates, or also the contrails. All those things matter. Then step 5, you need to again do a forecast. What will happen to noise if we build a third runway? What will happen to contrails, and what happens to CO2 emissions if we build a third runway? Again, it's as strong as your model. Then week 6, 7, and 8, you need to monetize all these things. You need to express these things in pounds and pennies. Add it all up and calculate a net benefit. This seems simple, right? We're just going to add it up. It's not at all simple. Because once you start aggregating, you lose information. So if everybody in this class gains £100, that is worth, that's 30 of you, that's £3,000, right? If I gain £3,000 and you guys gain nothing, that is also £3,000, right? But it is a very different outcome, right? And presumably you guys would appreciate it if you got £100. Which actually reminds me, Hussein, Tia, and Alfie, if you're here, I got chocolate for you. I'm not wearing my glasses, so I can't recognize you. So aggregation actually hides information, and at this point, distributional concerns get lost, right? Then you need to discount everything to today. We talked about that. And then hopefully by this time, typically projects have run out of time and budget. You need to perform a sensitivity analysis. What if all the assumptions, all the choices that I made were different? Do I still support this project, yes or no? And then finally, and that's the simplest step, recommend the alternative with the largest net benefits. So let's look at a case. This is actually George McCarran who developed this. Does London need a super sewer? The problem in London, and the sewerage in London, is that this is essentially Victorian, and the city has changed a bit since those times. And one of the proposed solutions is the super sewer. So one of the issues with the London sewerage is that it carries both rain and human waste. And that means that if it rains a lot, everything gets dumped in the Thames. So what we've seen a couple of times in the last few weeks is heavy rain over London, and the consequence is that the contents of people's toilets are just dumped untreated into the Thames. And that used to happen around 60 times a year. Because of climate change, it is likely to happen in the future. Now, this is not good for you. It's not good for fish, because of all this stuff, all the nutrients essentially kill a lot of fish. That is what you see in the bottom picture. It doesn't look good, birds floating in the river. It also is pretty risky for human health. This is David Williams, who thought it was a good idea to go swimming in the Thames, which it is not, guys. Don't do this. Actually, you should not be swimming in English waters at all, because our sewage treatment is pretty bad. Rowers suffer less of a problem unless you fall into the water, but definitely don't go swimming in rivers in the UK. Just don't do it. So the solution that they thought of was to build a super sewer. It's a big tunnel, as you can see here, that will take all this shit essentially under the Thames and into Surrey. There were actually various options that they have. They could upgrade the existing treatment plants, they could build new treatment plants, or they could just ship it all out to south of London. So the first step that they needed to do is to find these particular solutions, then define a baseline, what would happen otherwise, not good. Essentially the way they solve the problem at the moment is that they send out little boats called bubbler and skimmer boats that essentially scoop up all the shit from the river, which is not a very pleasant job, and it's not very effective because it sort of dissolves, and it's not that it keeps steady or anything. So that doesn't do a whole lot. Then the third question is who has standing, whose benefits, whose costs. The original project that they proposed, or the original analysis that they proposed, they actually only looked at what happens to the customers of Thames Water, and it didn't bring any benefits. So then they expanded it to the whole of London, and then they forgot and were actually going to ship all this stuff to Surrey, where of course it would be treated. So it also affects the people in Surrey, right? So initially they said, yes, let's look at London, right? Until somebody said, no, it's not fair, you're dumping a lot of stuff on Surrey, so perhaps we should include those people as well. And this of course completely changes the calculus, right? Because now you have the significant and fairly substantial negative impacts of having additional treatment plants in the Surrey countryside. So that matters, right? Who has standing? And then you need to identify all the potential impacts. Now the things that they looked at, and this is important, is the things that were included as benefits were fourfold. One, they don't have to send out bubbler boats, not blubber. Second, they looked at visual amenity. The Thames would look better. There would be fewer days that it would be absolutely stupid to go swimming in the Thames, and fewer fish kills. Frogs don't matter, right? Apparently. Also, other health impacts do not really matter. Things that happen downstream in the estuary of the Thames don't matter, right? So such things as algae blooms in the channel, completely disregarded. algae feed on human-based, right? Um, so they limited this to the things that were most important to them, or more probably they limited to those things that they could quantify. Because recall, we're doing forecasts of what would happen if we do this project. That means that you have to have a model that predicts those consequences. And those things that could not be predicted, say algae blooms in the Thames estuary, were not included because they did not have the expertise to model this. Not because it was not important, or it is not important, but they could not quantify it. And this, of course, is crucially important for the outcomes, right? What is included and what is excluded. Some of these things I've mentioned, and actually George came up with a whole bunch of other things that were excluded from this, like the vibration from construction works. They're digging a huge big tunnel under London that causes small tremors, and those small tremors can damage buildings, right? So people would have cracks in their houses, and so on and so forth. And of course, because London is a pretty old city, there's all sorts of nice archaeology under London. And by building a big thing through it, some of that was destroyed, right? I've given away the answer already, right? They are doing this. I talked about this. We predict the scale of the impact. They did it over 50 years. Somebody, somewhere in an office, predicted for 24 alternative projects, including no project, so 25 scenarios, how many fish would be killed in the year 2047, right? That is a necessary part of this cost-benefit analysis. Okay. In public policy, there is a tendency to underestimate the cost of things. And this is guidance from the Treasury saying that actually you should be careful here, and really you should, if companies say they're going to do it for 100 million, then really you should not believe them. And here is the guidance that depending on what's going on, you should either add 4% to this, or 1% is the lowest, and sometimes you should just triple the cost estimate that those companies that promise to do this for you are going to give it. And we've seen it time and again, right? The current one is the high-speed line to Birmingham. The costs just keep increasing and increasing and increasing, and I think they're now around 10 times the original budget. The same for the new nuclear power plants that are being built in Somerset and other places. That by now the cost estimates have tripled, and it actually will, the Hinkley C was supposed to have started working 2 years ago, and now they're thinking, well, maybe 2028 we'll get it done. This is the nature of public projects, right? And partly this is because these things are hard to predict, and partly this is smart behavior on part of the companies, right? So the civil service is obliged to give the project to the lowest bidder. So it is in your self-interest, if you're bidding for a government contract, to lower your cost estimates, because then you have a greater chance of winning it. But then once you've entered the contract, you essentially have a captive customer. Because at every point in time, the question is, do we give them a little bit more money? Do we increase the budget? Or do we walk away and start all over again, right? And walking away as a government and starting all over again has two costs. One, you start all over again, so it is much more expensive because all the money that you paid to the first company is lost. But also, this is egg on your face as a politician, right? You champion this project, and now you have to abandon it and start all over again. That is a great risk to your reputation. So that is why these things tend to escalate. Step 6, monetize those impacts. So they came up with some numbers, right? Health risks are 38 pence per person per day, not per day. Fish scales are worth £1.51 per event. And in week 9, we'll come back to why is that per fish scale rather than per fish? Why aren't the fish counted here? But here you see some numbers, then you need to discount everything. And here you see the equations. This is just a reminder of the importance of the discount rate, right? So 100 pounds invested for 100 years is worth 799 pounds if you use an interest rate of 2%, 2.1%, but it's worth 3,100 pounds if you use an interest rate that is higher, right, 3.5%. So the discount rate is crucially important because it's essentially exponential, right? So things that happen far in the future are worth very little, and those changes can be quite big depending on the discount rate used. Add everything up. They found that the net benefit of the super sewer is somewhere between 3 and 5 billion, so they decided to do it. I don't think they did a lot of sensitivity analysis. So here are all the things that regularly go wrong, right? 3 minutes left. And I think I addressed them all. Excluding important impacts, talked about that. Measurement errors and forecasting errors, talked about that. Evaluation errors, we talk about later in the module. Strategic errors, we've seen a lot of that during the Brexit debate, right? That there's always people who are willing to conclude what you think they should conclude. Minford here is the prime example in the Brexit debate. It's not that Minford is dishonest. It's not that he deliberately changes his conclusions based on the client that he has. But you know that if there's 5,000 academic economists in the UK, you know their opinion about Brexit, and there's this one guy who you know will support Brexit, then that is the guy you're going to hire, even though he has no expertise in this particular area whatsoever, and you're going to ignore all the true trade experts that are out there, right? That is how you find an economist or hire. It's not that these people are dishonest. It is they are selected because we know what they're going to say, right? And that is, of course, something that happens all the time. It's not that these cost-benefit analyses are done outside of political pressure, right? And there's many, many things that can go wrong. And as George rightly put out here, in some cases the decision has been made already, right? And the cost-benefit analysis is done to justify the decision rather than to guide the decision. So, all sorts of things can go wrong. All sorts of things can go wrong. And then step 10 is actually the easiest one. You actually say, well, this is what we found. And as I said, the super sewer actually is being built at the moment. This slide is a few years old. I don't think they will be quite ready next year, but they are definitely digging that tunnel at the moment. So this is just to wrap up. Cost-benefit analysis is a very powerful tool if you sort of want to bring discipline into the decision making on complex decisions. You need something like a formal decision analytic framework. At the same time, you put things, there's all sorts of ways of abusing this, and people are very aware of this. And as a result, the theoretical advantages don't always overcome the practical disadvantages. That's all I wanted to say.